ready to start the next session of DevCamp 8, 2nd November. This is going to be primarily Nastasia today. So very happy to have her here. Nastasia is going to start with a presentation on validation. For those who are listening or those who are here, I think it is one of the most interesting topics because so like Holochain, what differentiates it from some of the other storage technologies out there is validation. And I think validation at a group level or micro network level is really new. And I've always found it fascinating from an architectural perspective because I find we're constantly thinking about it wrong or making wrong assumptions. And then, they get called out, which is very cool. And then post break, we'll do a session where Nastasia is going to share the code from our repo. But yep, over to Nastasia first, and we start off with validation.
Thank you, Sid. Just a second. Yeah, I would share my screen.
Sure.
Okay. All right. So today we're talking about validation and how it's different in the Holochain application as compared to decentralized application. So first one is the functions that validation plays in Holochain apps. First function is the one that you all would be familiar with, is about maintaining the business logic integrity. For example, if you require your username to be 5 symbols and more, this is where you implement this logic in the validation. But the second function that validation plays in Holochain applications is different because it maintains the network integrity. And it's not about verifying the input that you have from the user interface. It's more about verifying the data that you receive during the gossip from other nodes and making sure that you are still in the network with the nodes that are valid and that are executing the same code as you are. So with this being said, there are 2 steps to every validation process. First, as we have learned on the previous sessions, once an agent creates some piece of data that is to be published onto DHT, first, this piece of data is published onto their source chain. So this is happening locally. And this is where the first step of validation happens. And this is where we ensure that user doesn't create the wrong data, basically ensuring our business logic. But the second step is about making sure that data that you have received from the network satisfies the validation criteria that every agent on the network also has. So you execute validation for your data, and then you execute it for the data that you have received from other agents. And to illustrate this in an easier to understand way, so we have a user who creates the data that goes first onto their source chain and then gets published onto the DHT. So while user is creating something on their source chain, we are basically validating our business logic, not allowing user to create something that's wrong. And then second, we are validating the network integrity. So with validation being in process, there are some things that make it different from any other DHT operations that we would be doing. First of all, since validation is executed multiple times by multiple users, it has to be very cheap, because otherwise your application would be creating a constant CPU load every time that it's being executed by any agent. And second, and this is very critical, validation rules have to be deterministic, meaning that it doesn't matter what agent is executing them and what's the state of their network is, in terms of having or not having access to the data. The result should be the same. And since rules have to be deterministic, we have certain restrictions. For example, we have to use special functions for any data retrieval that we would be showing today during the code review part. And second, we cannot rely on links retrieval because links are not deterministic. And the thing here is that when we are trying to get links from the DHT, we are always talking about getting a set of some data. And for this set, it's never possible for us to be absolutely certain that we have received a full set or not. We can only be certain about receiving 0 links or receiving non-zero links. But there is no guarantee that if we receive set of, let's say, 5 links, that there isn't a 6th one that we didn't just get because data propagation didn't happen. So when writing validation rules, we can only retrieve specific entries which we identify by their hash. And then, so with that being said, for any entry that we're validating, there are 3 possible states from the perspective of validation. First one is an entry is valid. Basically, rules have executed, they have verified that it complies with all of them, and so entry considered to be, correct. Second is entry is valid when the rules are broken. But there is a third one, which means that entry has unmet dependencies. And it could happen when your validation rules are relying on some external entry, something that we would be showing today. And this entry isn't yet available to your agent. So you already know the hash that you want, from which you want to retrieve the data. But when you try to retrieve it, you receive nothing, which means that you would be waiting. Your conductor would be waiting for this validation rule to be executed later using the exponential backoff to make sure that you don't just waste your CPU on a cycle for validation attempts, which happens too often. So eventually, every entry should be either valid or invalid. But there would be often times when entry would have unmet dependencies, until which it wouldn't be considered like a proper entry. So with validation rules, we have the following consequences. First one is that in a holochain application, you cannot actually hide the fact of breaking validation rule from other agents. They would be able to know this. They would have access to this data regardless of your application design. But if you're worried about your users mistakenly breaking your validation rules and mistakenly committing some wrong data to the DHT, and then being known by other agents as somebody who committed the wrong data, you could write additional logic in your application that would allow you to decide how to handle this event. So you always have this data, but it's up to you to decide how to handle it. During the previous DevCamp, we've discussed examples with, let's say, grandmother mistakenly committing some data that she shouldn't be committing. But then if you are using the same DHT as your grandma and you know that it's actually her, then you as an agent who is participating in this network can, being fully aware that you're communicating with the agent who committed the invalid data, make a decision that still you would allow her to share some data or do some other action. So you can fully expose this data to your users and allow them to make decision as well. And when it comes to the execution of validation rules, this is how it happens. I'm just going to give a short overview. Code would be shown later. The conductor is always in charge of executing the actual validation rules. And in order to do this, it uses the callbacks that are up to you as a developer to define in your application. So you are not required to define all possible callbacks for every application. It's rather the opposite way. Like you can define as many callbacks for entries that you have written, and every callback that you have defined and exposed in your Zone API would be executed by the conductor. But by default, there are no validation rules that would be applied to your entries if you didn't write any. So that's a very short overview of what validation is from the technical perspective and how to work with it as a developer.
Stephen's asking, interested to know why unmet dependencies and not a return code for invalid? Is it because it's such a common use case that it was deemed worthy of doing?
Yeah, that's a great question. And I think a very important distinction. So holochain is eventually consistent, meaning that at any point in time, you cannot be certain that you have all data in the application because network, delays, all of this. So if you do not have the data yet, you cannot say that this is invalid because once you receive the data, you actually, if you have an entry which relies on some other entry to validate it, if you do not have this dependency entry, you cannot say that this entry is invalid, because then once you receive the dependency, you would have to rerun the validation, and you would go back and maybe say, hey, this is actually valid. So it's not, think about it as knowing that something is true, knowing something is false, and then knowing that you do not know if something is true or false, basically undefined. So that's the third state for unmet dependency. It's undefined. We do not know yet what would be the result.
It's a very humble position to take. I think we have one or two questions coming up. I can see people typing. Nastasia, do you want to share some examples of what you've learned, like things not to do in validation that we don't initially think of, but as you get into Holochain, it's like, oh yeah, of course, that's stupid.
Yeah, so the first thing would be, Guillaume mentioned it a couple of times, and then I realized it for myself, that validation is actually part of your data model. So when you think about entries that you would have in your application, you need to think not only about the relationships between each other, but also about how would you be validating every single one of them. Because, for example, if you may decide to not use links because they would prevent you from validating your entries. Or you may decide to implement different business logic because you cannot implement something difficult in validation. And that's basically an example from the DevCamp. Originally, we wanted to implement a validation that would allow us to make sure that every player only makes a single move for every game round. But the problem is that every game move is connected to the game round by links. So if we wanted to implement this logic, that would have been something like this. I mean, my primitive idea. We would get the round entry, and then we would query all the moves connected to this round entry by getting links. And then we would count number of moves made by every agent in this set of links, and then we would make a decision. But the problem is that link set is not deterministic. So we cannot make any validation decisions based on the number of entries we would receive from these links. So instead of doing this, we had to implement additional business logic, which we've shown you previous week, I think, where we allow users to make multiple game moves for every round, but then we only take a single move when calculating the results. So that's a workaround. That's not the best way to do this thing, but it allowed us to implement kind of the same business logic without going into trouble. So that's the main thing for me. And then what not to do in validation. I think I've already said about it, like validation has to be cheap. So when you think about algorithmic complexity and memory complexity of your code, your requirements for optimizing code would be higher when you're writing validation functions as compared to the rest of your business logic. Like, it's okay if something that users only do occasionally, maybe sign up for an app or do some action in there. It's okay if this step is taking some resources or like allocating a lot of memory or is very heavy on CPU, whatever. But this step cannot happen in validation because that would make your entire application very slow and resource demanding. So that's my main lesson.
Do you want to share, maybe even validation rules need to be limited to that DNA or that membrane? Like you can't have.
Oh, right. Thank you. Yeah. So every validation rule is only defined for the network in which it's currently being executed. But once in a while, you could have some use cases where you would want to validate something from another network. For example, let's say I have a profile in a network A, but then I sign up into the network B and I make some claim. Like, for example, I have an awesome reputation with 100 likes in the network A. And then I make this entry in another network. So validation rules in network B do not have direct access to validate any of my claims in this new network. So in order to make sure that I'm doing this right, I would have to write a business logic that would allow me to make this query into another network, verify that, hey, okay, yeah, she does actually have 100 likes. But yeah, that's another question about the design. When you want to have a separate DHT, you need to decide if this DHT contains enough data for you to verify its contents. Or maybe you want to include something more in there in order to be able to have those validation rules that are reliable and fast and can actually happen.
Thank you. We're going to do show code from our repo and then do some Q&A. Nastasia again.
Yep. Okay, so this is the repository where we've already defined the rest of our business logic, except for validation. So the first thing I want to show you is a helper function, which doesn't actually implement any business logic, but we would be using it in some of the validation rules. So I have defined this function to be a generic function, which means it would be generated for every data type, which is called O here as an alias, basically. And the data type O has a requirement that it would implement the trait try from. Basically, if not going into Rust specifics, it means that this function can only be used for data types which satisfy this criteria. So the function accepts a single parameter called entry hash, meaning that for this entry, we want to retrieve its contents from the DHT and then convert it from a holochain entry into a Rust struct, which would allow us to access its actual fields. So since we're returning a result of the Rust struct of data type O, we have a return value, which is wrapped as usual in the external result, inside of which we have an instance of this data type. So going into the body of the function, first line is an actual usage of the holochain function, which can only be used, which is specifically made for the validation, meaning that this is a must get entry. This function is different from get entry because it's adapted to validation to be deterministic. And then if it doesn't retrieve anything, then this result can be handled by the conductor being processed as an unmet dependency. So we retrieve the entry, and then once we do it, we basically just unpack this entry into a data type that we want to. So we access its in a field where we have the data, supposedly. So there are two branches of this match. First branch is when we actually have the data inside, in which case we try to convert from holochain entry into the entry of data type O, and the conversion happens here. And then if the conversion is successful and we receive the result of OK, inside of which we have the deserialized data, we just return this deserialized data. But if for some reason we receive an error, we just propagate this error further into the chain of functions that are calling the current function. And lastly, the second branch of this match is when we try to get an entry from the whole chain. We try to access its inner thing, but then there is no entry. In which case, we would return from this function with an error, which would be saying this thing. So that's basically it. That's a simple act of retrieving something from DHT and then instantly converting it into the Rust structure. With that being said, we can now go into the actual implementation of validation functions. I would start with the GameMove because it's the one that allows me to show example of different validation things. So first validation function which I want to implement is this one, which would be executed every time anybody on my network tries to create an entry of the data type GameMove. Name of this function is, I don't know how to say it in English, honestly, but basically it's a composite thing, meaning that if by any, for any reason, if I want to write a validation function which would be applied to any action whatsoever made with a game move, then I could just remove this create entry in between and have name of my validation function to be like this. In which case, this would be the same function which would be executed on creating game move, updating game move, and deleting game move. But in our application logic, we actually want to differentiate between those three actions, which is the reason why we're writing it in such a detailed manner. So every validation function, regardless of how you name it, how detailed it is, it always receives the same kind of parameter, which is a validate data. This is a struct which contains certain data about thing you're trying to validate, including the contents of the thing that you are trying to validate, and some metadata as well. And as a result, all validation functions return the same data type, which is wrapped in external result, and inside it's validate callback result. And it basically has the same like states invalid and valid. But then the third state of having unmet dependencies is handled differently. This is because if this function is able to finish, then we can be certain that it's either valid or invalid. But when we have unmet dependencies, it means that this function itself wasn't able to finish, so we are in the unknown space. So inside of the validation function, first thing that I'm doing is I'm using the try from element that I have just shown you from the utils in order to convert the thing that I have in the validation data into an actual game move instance. That's because I want to access fields of the game move in order to implement my logic. And for any game move in our game, we want to make sure that players are only consuming the non-negative amount of resources. So we allow them to consume 0 resources, but consuming negative amount of resources doesn't make any sense. So we are forbidding it. And notice how in the case of invalid data, I am still returning an external OK. This is because even though we deemed the result, the game move entry invalid, this happened during the normal execution of my validation function. So from the Rust perspective, nothing is wrong, so we are returning an OK result. And then inside of this OK result, we are returning our basically verdict decision about this game move entry, which we deem invalid. And here I'm just providing a nice comment, which would allow you to understand better what's happening. So it would be useful during the debugging, testing, whatever you do with this. So now we validated the most basic thing. Next step would be to make sure that a player who is making this game move is actually playing the game session for which game move belongs. And given our data model, we would need to do 2 more requests here. So first one, we would be retrieving the game round. Oh, by the way, sorry, here I'm not actually making any queries to DHT. I'm just converting element which I have in the validate data into the game move entry. So that's operating with the locally received data. While here and here, I'm actually making queries to DHT. Hence the must get name in the beginning. So these are the 2 steps where our game move entry could have unmet dependencies. For example, if you already are creating your game move, but you do not yet have the entry of the game round or game session to which this game move belongs, this validation function would have to be executed 1 more time or a few more times until you get those dependencies. So assuming that we do get those dependencies, and now we have the Rust structures to operate with them, because this one returns the game round and this one the game session, we can now check if the list of players for the game session actually contains the owner of the game move. Why do we want to get the game round, you ask? That's because every game move doesn't have a game session hash for redundancy. We decided to do it like this. So we have to do this additional step. as an alternative, you could define a game session entry hash inside of your every game move, and then you would save this step, but you would still have to do this query in any case. So we are checking that in the list of players for the game session, we actually have the agent who is the owner of the game move. And if this agent isn't there, once again, we're returning a result wrapped inside the OK, because this is a normal execution of our function, and say that this entry is invalid. And this is just an error message I return here. And as we get to the end of this function, since all of our conditions have been met and we've been able to execute to here, we just return the valid, meaning that this entry is considered to be valid after all of these checks. So that's for creating entry game move. But there are other things that can be done with a game move entry, saying that we can update them and we can delete them technically. However, for this game specifically, we decided to forbid our users from doing any of those actions, meaning that nobody can update their game move entry and nobody can delete their game move entry. And in order to implement that kind of behavior, we are writing the validation functions, which you see here for update entry and for delete entry. And then inside of them, without any conditions, without any checks whatsoever, we just bluntly return invalid, meaning that everybody who tries to do this action would run into the problem of invalid data. And since validate data isn't actually used here, I'm using the underscore instead of the actual variable name, just to make the Rust compiler happy and my code smaller. So yeah, that's all of the validation for the game move entry. But there is another nuance. I have just defined those three functions here, and they are just some functions right now, which are not known to the whole chain conductor. In order for them to become the callbacks which would be actually used during the application execution, I also have to go to the lib.rs and write those things here, basically providing the wrappers, which are calling my functions from the game move module, have the same signatures. Basically, everything is the same, only here I am applying the HDK extern macro. As a reminder, you do not technically have okay, sorry about that again.
You were bumped out of the network.
yeah, indeed I am. Okay, can you see my screen?
Yep.
All right, so I've been saying that in order to expose these functions I have defined right now as actual validation callbacks for whole chain conductor to be aware of, I need to apply the HDK extern macro. And I wanted to remind everybody that it's not technically necessary for you to define those wrappers like this. I could just copy this macro from here and apply it to here, and it would also compile. It would work the same. It's the developer experience that's different, because if your project is big enough or you're reading someone else's project where you do not know anything that's happening, it's useful to have the entire API definition in a single file. So that's more about convenience rather than technical requirements. Once I add those definitions of my validation functions, I can now launch my application and be certain that these validation callbacks would be called. So that's all for the game move. And now I want to show you the game round validation as well. Let me scroll. Okay, so for the game round validation, I want to validate the step of updating game round entry, and I want to check a number of things here. First one is similarly to the game move validation functions, I'm implementing this one. You can know the name is the same pattern, like validate underscore name of the action, update entry underscore name of the entry. And if you are questioning, like if you're asking where does this name come from, it's actually the one we have defined here. So I mean, if I written something different here, I will have to change my validation function names as well. So going back to the function, we have defined the signature, which is the same one. And here I am, instead of using the helper function, I'm just, this is another way to do the same thing, to convert the validate data entry into the game round entry, which I'm doing with this bunch of code. So for the game round, for an update of the game round, first thing I want to validate is to make sure that we are not creating more game rounds than there are actually rounds in the game. And since we've already explained that new game rounds are created as an update, which is committed to the round 0, it means that every time we, from the game logic perspective, create a new round, we are actually committing an update entry on the previous round, which is why all of this logic is implemented here according to applied to the update entry action. So I have the game round entry, which I need to retrieve this session field. And using the session field, I'm making my first query to DHT in this function, as a result of which I would receive the game session entry. And I need the game session entry in order to execute this line of code and to get access to the number of rounds which is provided for the game session itself. So we're making sure that the current round number of the update that's trying to be committed, that it's not bigger than the number of rounds in the game itself. If it is, then we are returning the invalid result and explain that this is the round number. So that parameter goes here, and that parameter, this entire thing goes here. That's the Rust formatting for strings. So, okay, we validated the first thing. We've made sure that number of rounds would be according to the game parameters that we have defined. The next thing that we want to do is we want to check the previous round number. So this code here only allows us to make sure that we, at any moment in time, wouldn't create a round which would have the number bigger than the game session. But it doesn't help us to validate that our chain of rounds would have the right sequence. So if we only get to this line, it's absolutely possible for us to create a chain of rounds which would have numbers like 0, 5, 3, 10. So there wouldn't be any ordering or sorting for these numbers. In order to validate this, we need to get access to the previous entry to which we're committing the update. And we're doing it in all of this code. So first thing we do here is we are getting an update header. We're doing it because every update header has a reference, allows us to access the previous entry in the update chain. So we're retrieving this update header from the element we receive in the validate data, and then we match its contents to these two branches. First branch is the one we're looking for. This is when the header is actually an update header, in which case we can see the type of the header update, and then inside of it would be the data of the previous entry. The update data, which contains a few things. And the first thing we do with this data is we make another DHT query using must-get-entry struct, trying to get the actual contents, the Rust structure, which would contain fields of the previous entry. Once we do this, we have this data in the previous entry, and now we can validate that previous entry round number plus 1 has to be equal to the round number of the current round, meaning that our round update chain would be monotonically increasing by the increment of 1. And if that's not the case, once again, we're returning the invalid result, providing a detailed error message explaining how we have this round number, but not that round number, and that would help people to understand what's happening both from the user interface and the debugging perspective. And this is the second branch, which basically Rust compiler requires us to provide. We have to cover all possible options. So in the unlikely event of this header, for some reason, not being an update header, we would return that kind of error. I wouldn't expect it to be a frequent case at all, but like this is us following the standard Rust procedure and writing the code that wouldn't have unexpected cases which it doesn't know what to do about. Once we validated this thing, we are once again returning the valid result, meaning that this update of the GameRound entry is actually valid. So I think with this code, I have covered most of the cases. We know how to make queries to DHT. We know how to get access to the previous entry in the update chain, which would come in handy in most of the cases. I mean, in some cases. And we also know how to get the data that we receive without any DHT queries and run some logic verifications on it, like we are doing with the GameMove, for example, right here. So yeah, that's, I've also added a few lines of comments here for the GameRound, for example. So if you want to try your skills or your understanding of validation, you can copy the same approach, but for the different things. So for example, our application would benefit greatly from also having validation for creating a game round. Because first of all, in our logic, we want to make sure that creating entry of the game round only happens with a round 0, meaning that round number has to be 0, otherwise it's not valid. And then another thing we want to verify is that the station state for which we're creating the round 0 is actually in progress. Because if the session is already finished or lost, it doesn't make any sense to create round 0 for it. I mean, the code for implementing it would be basically repeating the things that I have already shown. So in order to have some time for Q&A, I decided to skip it here. But you're welcome to try to implement it yourself, and we can help you answer your questions about writing this code on Discord.
And we will see you in a couple days on Thursday. And 1 hour prior to what we started today.
Yeah.
Yeah.
See you all.
All right.
Bye-bye.
Bye-bye.
Thank you.